Hi there, how's it going? Welcome to another episode of Brain Training, a place where I train my English by explaining LeetCode solutions. And today we are back again with a sorted and array. The question asks us to rearrange the numbers in the integer array in ascending order, which means place the numbers from the smallest to the largest. And I have been doing this for a while now. I cover all the quadratic time algorithms that I know. And today we're going to tackle this using Quicksort. Okay, Quicksort is really tricky, really hard algorithm to digest because it have two parts. So we're going to start by the first part, which is called partitioning method. And for this version, we're going to implement the easiest one, which is called Lomodal's partition method. Okay, that's one of the difficulties of Quicksort is that we have different ways to implement this partitioning method. So we're going to make this private. So the method we're going to name this get correct position. This method will take nums, the int array, and the range, the start and end range, which we're going to iterate over this in this array. And we're going to return an int value, that it is the correct position. That's it, simple as that. That's the function signature. So now the first thing we do here is to select the number we want to place in its correct position. For this example, we're going to use the last number in the range, which is in the index end. So our number is 2. That's what we did so far. Next step is to declare a variable that will hold the correct position. We're going to call this CP. And this variable will start at the start position, the start range. So CP is right over here. Simple as that. So this is the variable that will hold the candidate for the correct position. You will see what I mean by that. And now we have everything in place. We can start our for loop. Just one for loop. We're going to start from the start until the end. So here until in Kotlin, the last index, this end position would not be included. So we're going to go from 0 to 5 actually. Now is the time to place the number we choose in its correct position. How we do this? We're just going to move everything. So what we do is we move everything that is less than our number to the beginning of the array, of the beginning of this range. So we do this by checking the nums. So the number at position I is less than our number. If so, we have to move this number to the beginning. How we do this? Swapping. So we're going to do this by nums swap I. So the number and the position we are checking in with our current candidate correct position. That's what we're going to do, because so far in the beginning of this array, in this example, the candidate for the correct position is 0. But we find in this moment here, we find a number that is less than our number. So this number must be in its wrong position. So we're going to move this number to the beginning of the array, which is index 0 right now. And after that, we're going to update our correct position candidate. So we're going to move one step forward. So let's give this a try. Let's give this a run. We're already in a good position here to start a walkthrough. Is the number at index I less than our number? It is not. So we're not going to enter here. We're going to move forward. Is the number in this position less than our number? It is not. is greater. Is the number in this position less than our number? It is. So we're going to send 1 to the beginning of the array by swapping with CP. So 1 is going to be here, and 8 is going to be here. It's going to be here, right? And we're going to move CP 1 step forward. We just run this portion over here. Next step for I. So the number at index I still is not less than our number. Next position, the number in index 4 is less than our number. Our number is 2, by the way. Remember that. So yeah, 0 is less than 2. So what we're going to do, swapping places with between 4 and 1, the index that I, the number that I is pointing, and the number that CP is pointing. So 0 is going to be here, 0, and 3. And we move again, update CP to our next correct position candidate. Now is index 2. And we keep moving I to the last iteration. 10 is less than 2. It is not. We do nothing. So here we break this loop, and now we are right over here. That's the point where we are. And this is our variables setup. So CP is pointing to 2, which means this 2 is the correct position of the number 2, by the way. And what we're going to do is place our select number that right now is in the end of the range of this array to its correct position just by doing a swap. So this is the last swap we do just to place our number in its correct position. So we're going to do a CP swap with end because our number, as you might remember, is in the end position. That's what we do here. Swap CP with end. So in this moment, we take the number or a number that we choose, place to position 2, and the number that was in position 2 go to the position end, to the end position. And that's it. This is how the models partition method works. And now we have the hard part, which is the recursion, right? What recursion does. So let's implement this. So we'll have fun. Let me do private fun. We're gonna call this Quicksort because Quicksort's just the recursion part. And Quicksort takes the same parameters like the int array, a start range and end range, but doesn't return anything. And because Quicksort is a recursive function, we need a base case to break the recursive calls. So if start point, start range is greater or equal to the end, that means we are out of bound. So we should break this loop. With this base case in place, we are good to call the get correct position function, passing exactly the same parameters that we got. After this, with the correct position, we can call our Quicksort here. We do the recursive calls, but passing the same array, but this time the start point. So this is gonna be the left side call from start, but in the beginning will be position, the correct position, -1, because we want to remove the position the number that is already in its correct place. And then the right call side nums. So this is going to start from the correct position +1. Again, it's keeping the number that is already in its correct place to the end. So right side call. That's how we do the recursive calls, and this is how we skip the number that is already in its correct place And we are good here. Just a minor detail for Kotlin side, I have to implement the extension function that I'm using here. Swap. We don't have this in Kotlin as far as I know. Maybe we already have it, but I always do this extension thing. So first thing we have to do for swapping is the temp. Save one of the numbers. In this case, I will save I. Then we are good to replace I with J. And then J with temp. Oh, yeah, this is J, not CP. I and J. That's the two numbers we receive. I think we are good here. And finally, we have to call Quicksort in this top function. Quicksort will start nums 0 and nums last index. That's the range, right? This is the same range we are passing here. So that's how we implement it. Let's see this running. See what we got. Let's see if I didn't mess anything up. You already have oh yeah, I have to return. Forget this. Let's try again. More exceptions. Okay. Totally forgot about how to declare variables and how to declare parameters in Kotlin. So this is an int. This is a int. Int. Yeah, I think. Yeah, now we got it. So let's submit this to see what we got from the. How is the performance of this version of Quicksort? And as you can see, it's really bad performance, really poorly execution. Has a poor execution, a poor performance. So why we have this bad performance is because in a sorted array like this, Quicksort, we always going to select in the last number. So here we select 9, and we're going to run our algorithm. So we're going to check if the number we are looking at is less than the number we choose. Is this less than a number? It is. So what we're going to do here, we're going to keep swapping numbers here in place because they're already in the correct position. Swapping for no reason because this number is already in its correct position. We keep moving and swapping. Moving is less, it is. Move and swap. Or swap and move until the end. But this is already in the correct position. And then by the end of this loop, we're going to check, we're going to move CP. Look, this is going to move CP one more time because every time we swap, we move I, and swap, we move CP to the next position. So CP will be here, and we're already in the end position. We're going to do another redundant swapping here and return the last position. That's what we're going to do. Okay, with this last position, the recursion will use this position. So the left side will be, we take everything here. So we keep 6, that is already in our correct position. The left side will take everything here, and the right side will be out of bound. Okay, so 6 plus 1 will be 7. This is out of bound. This is going to be a return here. So what happened here is that we're going to iterate over the entire array, not dividing work. We're just iterating every time in the entire array over and over again, just like the quadratic time algorithms. The whole idea of Quicksort is to divide the array, hopefully, into equal portions and run the same algorithm, the partitioning method, separately in each side. So we gain performance by doing this. But that's not the case with this approach, the modus partition. The better approach will be the horse partitioning method, the original one. Horse is the name of the creator of Quicksort. So we're going to do something like this: fun get pivot position. This is a version harder to understand, but it's way more efficient. So let's start. This is the same thing. Look, take the same parameters, nums and the start and end positions that we're going to iterate over, and returns an integer. Just like Lumodals. But the first difference here is that we're going to select the item at the middle, a number at the middle. So let's see. First of all, we have the middle. So start plus end divided by 2 gives us the middle of this range. And we're going to select this number. We're going to call this number pivot, because we are not in this version of the partitioning method. We are not interested anymore in the item. We're not going to place this item in its correct position, or this number in its correct position. What we're going to do is we are trying to find the middle point where everything from the right, as you can see here, everything from the right is greater, and everything from the left of this point will be, or of this position rather, will be smaller. That's what we are trying to find. So let's see how this happens. So pivot will be the nums at the middle. So this is going to be the number at the middle. 6 divided by 2 will be 3. 3 is the mid. So here, pivot is here. Okay. So 7. This is our pivot. We're also going to declare now variables, 2 variables, one I. So we're going to use 2 pointers to iterate over this range. So I will start at start. Yeah, I start at start. J will start at the end. Good. So while I is less or equal to j, so while they are in range, they have to meet each other. That's the condition. While they didn't meet each other, we're going to do something like this. We're going to keep moving I forward. So while nums at I position is less than our pivot, we keep moving I. What that means is while all the numbers in the left side are less than our pivot, we are fine. We will keep moving I. Another thing we do here is while. Now we're going to move j. So while number at j is greater than our pivot, that means that this number is in its correct position. We move j backwards. Keep moving j backwards until they meet. That's the goal of these 2 pointers. After breaking these 2 loops, one thing could means that these 2 items meet each other. So if I is less or equal to j, if they still meet each other, these 2 they are not out of bounds, we're going to swap. We're going to run the swap. So we're going to, same thing, nums swap I and j, because that means they are in the wrong position. So that means that the number at left should be in the right and the other way around. And after changing the numbers, we're going to update the pointers. I move forward, j move backwards. Okay, so let's give this a try. Start by this while loop. This condition is already true, so we are entering this while loop and we keep going. So move I while I is less than pivot, and that's not true in here, so we stop. We just break this loop. We're not gonna move. So while j is greater than our pivot, we keep moving j backwards. And that's not true as well because 2 is not greater than 7. So what we're going to do here, this is still true, and we're going to swap both numbers. So change 2 to here, 8 to this position, and move I forward, J backwards. And we enter here again, checking, is this less than our pivot? It is, keep moving. Is less, it is, keep moving. Is less? Nope, is equal, is our pivot. So we stop here. J do the same thing. Is this greater? It is, keep moving. It's greater, it is not. So here we have this setup, and we check. This is still true. I is still less or equal to J, and we're going to swap. So 0 will be here, 0, and 7 will be here. Move I forward, J backward. And now this is no longer true, So we break this loop, and we are here. So this is our current setup. We have I, so everything from I forward is greater. Everything for J, everything after I is smaller, which means that I is the pivot position, is the position where we're going to change our recursion. It's the divide point of this array. So we're going to return I, just like this. I always going to be the pivot point, the pivot position, okay, in this version of Horace partitioning. That's what we do. We just return to the color side a pointer, a position where everything from that position on is larger. Everything before that position is smaller, okay? And what we do with this information, so we are here now, and then we have to change. Now we want to call the left side call. So left side call will be this call over here. We have to rerun the get pivot position in this side of the array, in this range of the array. So what we do is start position -1. That's correct. We don't need to change anything here, but here in the right position, we should include the pivot position. So, let me change this. Get pivot position. And it's gonna be PP. Not a good name, but you got it. We include in the right side call, we include the pivot position, because we have to rerun everything here as well. Let's run this to see what we got. Let me see if I didn't mess up anything again. Everything seems fine, and let's give this a try, this version. And look, the performance, much better. Yeah, the biggest problem with this Horace partition is that it's really tricky to understand how it makes the items being placed in the correct position, how to make the numbers, how this algorithm sort the numbers. It's kind of, I still don't fully understand how that works, but I just basically do it. Like I understand the steps, but I don't fully grasp how the algorithm achieves this. I tried to go to some walkthroughs to understand this, but come on, man, this is kind of stupid. So I like better the Lomoto's partition because I fully understand how the items are being placed in its correct position. But Horace, I just trust. I just implement it, and it just works. Why this works? I kind of understand that it's because of the recursion calls, and down in the line, some numbers will be out of bounds, and we will be left behind in this exactly correct position. But I'm not sure the steps. I'm not sure how that works, and take too much time to go through all walkthroughs to fully understand what's going on. So until the part of that we divide numbers, I fully understand. But how they will end it up in the correct position, I don't know. But yeah, that's it. That's Quicksort. I'll give this 5 out of 10. 5 out of 10. It's not a good algorithm at all. Really hard to implement, hard to understand, and yeah, I don't know. Bad feelings. I just want to get over with. Just want to get over with. It's not a algorithm that makes me feel good, and makes me feel dumb. This type of algorithms that make you feel dumb, sad. That's it. Bye. See you the next one. Hopefully.